name is Martin Müller. I work for Amazon Web Services on the Elastic Compute Cloud. In this talk, I would like to share some experience with a specific technology that we use to keep customer data safe in EC2. Some background about myself. I'm a principal engineer with AWS. I like to play with low-level stuff, synchronization, hardware, transaction memory, virtualization, real-time systems, microkernels, and last but not least, reactive security. Note from our company, we are hiring. We're building out an office as we speak in Lucas right now. We have engineering and internship positions there for systems people, kernel hypervisor developers, and for people that like to work on tooling and automation. Protecting customer data is our #1 priority at Amazon Web Services. And here I'm going to discuss one specific technique. I'm going to focus on the SAN virtualization stack primarily. I'm going to discuss how we address security issues at scale while maintaining availability for our customers. And I'm going to use a SAN security advisory as an example. First, let's have a look at what the SAN virtualization stack looks like. I'm using here a highly scientific diagram where gravity is used to denote layer dependencies. On top, you have 3 domains running. Those are the typical customer domains where you would put your workload in. They can have varying complexity and simplicity. Below that, we have DOM0 that's typically used to run the control software on SAN. In there, we have all the backend services that you would rely on. And at the very bottom, we have the actual SAN hypervisor itself. That is the piece of software that basically multiplexes the hardware and provides you the illusion that you have a full machine running on top of that. And the lower that you go in that whole stack, the more complex it is to address security issues because of the dependencies, right? You can't just take out a piece in this stack and hope that everything stays intact. SAN security advisories, or short XSAs. I'm going to introduce you to the format and the information that we typically get when we receive such an event. The advisories come with a title, a claim, and a number, and so on. They are typically embargoed. Usually the SAN security team uses a 2-week embargo process, but sometimes if information has been leaked before, or if the submitter has special requirements, we may get anything from 0 days to longer periods. First, you get a description of the issue that roughly summarizes what is happening and what goes wrong here. You get an impact summary. In this specific case, it's a serious issue because any domain can read any data on the system, could crash the whole system, and could even escalate its privileges and do anything with the rest. So this is a serious issue. You get information about which specific versions and configurations of SAN are vulnerable. In this specific case, everything starting from version 3.2, which is very loaded. So basically anything is impacted at the time when this was published. And usually you get a discussion of options that you have for mitigation. Sometimes you can run your system in a specific configuration to work around certain things. In this specific case, there are no options. So this is a serious issue. So one more thing that you get is typically a source code patch that describes how the issue can be solved, and that can be applied to build secure systems again. So how would you react to such a notification? Right? Obviously, you have to investigate what configuration, what version am I running? Do I have additional measures in place that might work around the issue? This one here seems to be pretty generic, so it likely requires an immediate response. How often does that happen? So this is a screenshot from the public web page where XSAs are discussed. And this was sampled a couple of weeks ago. At the very top, you see that we were at that point at number 245. Some issues are under embargo. These are the 8 ones on top, almost at the top without any links. The one at the very top is already publicly disclosed. That was a misconception and it was discussed too early on the mailing list. And below that, you have all the old issues. Right now, we get roughly 1 such event per month, and usually we get many XSAs per event. And the Zen security team uses a very well-established and reliable process to handle that and to communicate the issues, and the patches are typically of very high quality. Okay, so which components can be impacted by such a modification? Basically anything that is part of the virtualization stack, that means the hypervisor, this is the component that I'm going to focus on in this talk, but also QEMU, which is used for device virtualization, the kernel that runs from zero and provides driver backends, and anything that is used in the control plane, sensitivity, and so on. So what options are there? Maybe you have proprietary mechanism in your company to address specific issues. Sometimes you can change configurations, as discussed before, to work around certain issues. Obviously, you can take a patch, ingest it, rebuild all the patches, install them with reboot machines, but this is a very painful reaction mechanism for the customers because it incurs downtime. Then there's always live migration, sensitive live migration. But live migration at scale has various limitations. You have a small downtime when you copy the memory over. There's this one short time window where you actually switch the execution from one machine to the other. And at scale, you need a lot of empty target capacity onto which you can migrate, right? You need new machines that are built with the flash version onto which you can migrate. And there's also a technical limitation, live migration, with devices that are passed through to the guest. ACI pass-through is tricky because most devices do not support state extraction and state ingestion. So the remaining option is hot patching. That's basically an in-place modification of the code. That's a very complex approach, but if done right, it has the best properties for the customer. It's almost painless. So hot patching. If we ask Wikipedia, hot patching is the application of patches without shutting down and restarting the system. This addresses problems related to unavailability of services. So this is what we want. In our case, we need a binary patch against the Zen hypervisor version that is active on our systems for each machine. So when we started to look into this technology and develop that, the first question was obviously, is this already a solved problem? Has somebody built something like that, right? And we did not find anything that was directly a solution to our problem, but we found a couple of interesting sources of inspiration. The Black Hat community has a lot of experience with hot patching systems. They have a different angle in mind, so they are fine with losing 50% of the machines if they can take them over. So this is absolutely not what we want, but still the technology that they use and some of the approaches are quite interesting. Then there's a paper from 2009, it's almost 8 years now, Case Splice, which discusses an approach for the Linux kernel, hot patching for the Linux kernel. That's a very comprehensive paper that discusses lots of techniques that we can draw inspiration from. After we started to work on that, there were also newer efforts by Red Hat and SUSE, both aiming at the Linux kernel, which eventually were merged under the common name of Linux Live Patch. This was in 2014, and this has been developed since then. And in Zen itself, in the upstream versions of Zen, work started on live patching basically in 2016. It was experimental at the time, and this year with 4.9 on x86, we have a supported version of live patching. So, if you want to build something like that, what basic blocks do you need? We identified the 3 main blocks that you need, and these are roughly in order of use. The construction phase, where you actually take the source code patch and transform it in some way into the binary patch that you eventually load in the system. Then you need to bring that build artifact onto the target machine, and you need to inject that into the target address space, the Zen hypervisor in this case. And you also need to activate the code, so you need to splice it into the running system. Not just loading is sufficient, but you need to modify the existing code to make use of the new functions, basically. A lot more is required if you want to deploy that at scale, on the monitoring side and the deployment side and so on. But these are 3 main building blocks that I want to focus on today. So let's focus on the hypervisor itself first. What exactly is needed in the hypervisor? The injection and the activation of splicing. So I mentioned splicing a couple of times. What is that? It's the act of embedding code into the control flow of the active system. So let's have a look at the unit of splicing that we use first. When we started the project, there was a research project aiming at replacing the full hypervisor in one load. So they would basically load a new copy of the hypervisor to memory and then try to switch over. It was, we had a look at that and found it to be very complex due to the fragile serialization and deserialization code all over the place, and we found it to be hard to productize. The next option is you take very small machine code chunks that basically fix the issue that you are looking at in place, and you try to inject that in the target system exactly at the place where you need it. It sounds simple at first, but in reality you often do not want to just change existing code, but you want to add one more security check, one more if statement. So what you often need is you need to grow the code in place. And that is hard to do with existing active code. Also, if you want to think about how you automate things, how you want to automate the process of moving from the source code patch to the binary patch, you need information about the existing code, about the batches, the liveness, and so on. And that's really hard to obtain and interact with. So we found that approach to be a little bit too limiting. So there's a middle ground. If you look at function granularity, functions are easy to identify at all the different layers that we are interested in the source code, in the compiled object files, the linked binary, and in the running system. They have a very well-defined entry and exit point with a well-defined semantics, typically the cron convention. And this, working at it, this union simplifies the whole hot patch construction process. They are just the most natural union to work at, and this is what we choose going forward. So, how do we splice? We start with the original function itself. This is just a very small example function that has two pieces that I showed here, basically the prologue code in the very beginning. This is compiler generated and sets up a stack frame and so on. And then we have the actual functionality of this function, represented here by just one single conditional jump. What we do next is we load a replacement function. This is the function that has the fixed code. And in this very simple example, it's just the inversion of a check, right? So we replace the jump equal with the jump not equal. The prologue code and so on stays the same. What we do now is we choose the beginning of the old function. This is the one entry point that the function has. And splice in, poke in there an unconditional jump that redirects to the new function. On x86, this requires 5 bytes, 1 byte of code, and 4 byte 32-bit relative address. And the advantage of doing that is that we do not have to know all the call sites. We do not have to patch all the potentially many call sites. We do not have to understand which other code has taken a function pointer and stored it in some obscure memory location. We do not have to identify all those places. We instead take the single point where everybody has to go through. So this is simple. And unconditional jumps are basically free beyond microarchitectures. They are usually predicted and fully prefetched. So splicing, when can we do the splicing? Can we do that at arbitrary points in time? The first thing is obviously we can't change code that is actively being executed, right? Otherwise anything can happen on the system. So we need to quieten down the target system. Also, if we patch more than one function in one go, if we change the semantics of the system, we need to do that atomically. Otherwise, the system is running in a kind of inconsistent state with partially old code and new code that might not be compatible, right? If one function changes the semantics of the return value and another function consumes it, here you want to change both in one go. So, how do we make sure that this works? Sense compared to native code. So let's do a little bit of an excursion how function calls works at machine code level. You have two functions here. F1 is calling it F2. You have the CPU stack on the right, and it goes downwards on x86. In x86 assembly, the call mnemonic is used to invoke a function. So call increments the stack pointer, pushes the address after itself in the stack so that the returning function knows where to continue. Then control flow is redirected to the call target. And eventually in F2, the return instruction is reached. Return increments the stack pointer again, takes the address from the stack and jumps back to after the original call sequence. So coming back to web patching, we need to be careful about those return addresses on all stacks. Patch targets should not be on any live stack when we do the patching. And more specifically, no function that contains a patch target should, or no function that contains a return address should be on any of the stacks, because otherwise we would end up in an inconsistent system state again. We would return to an old function while other places already execute the new code. So how do we ensure that? In Zen, we can cheat a bit by using a special property of Zen. Zen doesn't have permanent hypervisor threads. When there's no activity in the hypervisor, when no one is doing a hypercall anymore, there's no active background thread in Zen. And all the stacks that are used inside of the hypervisor are empty or invalid. Their values are not used anymore. So this is a very natural state that we can explore here. In contrast, in the Linux kernel, that also has live patching now, this is not a property. The Linux kernel has active threads that run all the time. And when they want to do live patching, they have to resort to very complex techniques like scanning all the stacks to understand if there's anybody still actively executing some of the functions that they want to patch. So what we do here is we insert a global barrier right before the hypervisor turns into the guest operating systems. And in this barrier, we capture all the threads, all the CPUs basically to bring the system to a quiet state, and one CPU does the actual patching. We also need to make sure that this barrier doesn't block the system arbitrarily long. In case you have some activity in the hypervisor that is long running, like you terminated an instance and someone is still scrubbing the memory and it was a large instance and that takes maybe a couple of seconds. You do not want to block the whole system because of that. So what we do here, we add a timeout, and if we do not manage to capture the whole system in a quiet state within a couple of milliseconds, we abort this whole endeavor and return to userland and say, try again later. So after a couple of seconds or minutes or maybe hours, we can reattempt the hot patching, and then it usually succeeds, right? And we pick the timeout so that in the vast majority of cases it works, but in the very few cases where the timeout hits, we just retry later. And this gives us, that retains the real-time properties that some customers expect. So let's now switch away from the hypervisor to hot patch construction. This is arguably the most complex part of this whole tool chain. We basically start out with the source code patch that we get from upstream or that we develop ourselves in case we find an internal issue. And in the end, we want to have a binary hot patch that is built exactly for our target hypervisor and that contains all the fixed code, right? So how do we go from A to B? We have some idea what we need in a hot patch. We need two things basically. We need the fixed code on the very right. This comes from a new build. And we need some metadata. We need the name of the hot patch, the version, maybe some additional information and some activation code. So we have a source code patch that we get or construct, and we want to have a binary patch. So what we do is we take the original source code that was used to construct the version of Zen that we are looking at right now, apply the patch, make a copy, and then we build both sides. Right? You can also keep a copy of the original build process and just build the right side, but you need two builds basically. And there are more properties that you need of a build. I'm going to dive into that later. Then we compare two builds. We look at all the object tracks that were constructed and see which ones differ. We have an algorithm to understand the semantics of the changes of it. And And the outcome of that is a list of changed objects. You cannot just look at the source code and understand which objects are changed, because the build system plays a role there, right? You might have changes in header files that are sourced directly or indirectly in many places. The build system might decide to compile a C file in multiple places under different names. All of that is actually happening. So you really need to execute a build and understand what is changing. This is not enough, because in the end we want to look out individual functions and not whole object files. So what we do is we build the system again using a compiler switch to isolate functions in the individual sections. This is called F-function sections. And based on that, we can now compare and see which functions and object files have actually changed. So the outcome of that is a list of functions that we need to patch. This is typically exactly the unit that we want to patch up, as I mentioned before. So what we do with the list of functions, we generate some stubcode. The stubcode contains basically an init and an exit function that is used for activating and deactivating. And the stubcode calls into the splicing subsystem that we have. We have one more problem here. The Zen hypervisor is not really prepared to host modules in contrast to the Linux kernel. The Linux kernel has a well-defined API that Linux kernel modules can use, and the functions that are listed in that subsystem basically have a well-defined API. We do not have that here, so the compiler is basically free to arbitrary things with the code here. So we need to make sure that the hot patch that we construct is loaded exactly into the target hypervisor which we build on the patch. We can't mix those. So what we do is we generate a build ID that uniquely identifies one specific build, and we tag each hot patch that we construct with the build ID to make sure that we can only ever load it into its desired target system. On the right side, we now take all the newly built object files and take the list of functions that we want to change. We massage those object files, we rip out the functions that we are interested in, we cut all the references that hold the edit files together, and pull out exactly the things that we need, and then we link that together and relocate it against the desired target system. So all of that is a very complex process. I want you to take away two things basically from the slide. We compare build output to understand what needs to be changed, we do a binary diff basically, and this whole complex process needs to be automated, otherwise you're on trouble, right? You need to do that again and again and again for many different systems, for many different hot patches, so you really want it automated. Okay, let's talk about the generated module steps a bit. What other typical live patching or patching systems do is they create a list of all the places that they want to patch, or the list of activities that they want to do, and they embed that list into their hot patch, we load it, and the target system starts to work that list and starts to act on that. And if you design such a system, you can think about all the requirements that you might want to anticipate today and build that, and then you deploy that, and then you are stuck with that for the next 5 to 10 years because you can't update that because you don't want to reboot, right? This is exactly the problem that you want to solve here. So you have a time to develop versus time to use problem. It's quite typical from our experience in the last years that you have unforeseen requirements when you have to do hot patching. Maybe there's a change in the data structure and you have to do a once conversion. Maybe there's a cleanup required, maybe you need to clear a couple of bits in some certain data structures. Or maybe you need to run additional codes once after or before the hot patching, right? So all the time new requirements emerge, and if you have the static approach with the lists, you can't react to that. What we do instead is we generate the init and the exit code for each individual hot patch, and the generator for that lives in the build system, not in the target system, so we can change it. If we see new requirements, we can adapt it and generate new code there. Then we can load it with each hot patch. So this kind of design limits the risk that we will not be able to use the approach going forward. So I mentioned before that we have some requirements to the build system. Those need to be basically, we need reproducible builds, otherwise the binary comparison and diff generation is not meaningful, right? If we have a lot of noise in the build system with compiler output where we using a lot of randomized input, we would get huge differences and could not fetch. We could not distinguish random garbage basically or random changes from the actual fixes. So reproducible builds basically means for the same input you want to have the same output. What is the input here? Obviously the source code, right? If you change the source code, you expect changes. Also, all your tool set, your compiler, your assembler, your linker, all the libraries, maybe some other system components that you run in the build system, right? You want to tightly control it. The build paths. There are, at C level, there are macros that embed the path of the file that you are looking at into the object file. For example, typical debug code, there's an issue in file blah 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 line so and so. And if you compile the system in a different path, you embed the different paths and binary changes. And if the path has a different length, all the places after that change as well. So you have a doubling effect with a lot of binary change that is really not meaningful to you. So you really want to tightly control it. The time and the hosting variable. The Zen build system is explicitly set up to embed those two pieces of information into the binary so that when the hardware boots, it can really report which version am I and so on. So this is designed to be non-reproducible. We need to deal with that somehow. And if you do parallel builds, you might end up, depending on the target system, with different build order of individual objects, and those may result in different link order and so on. The Zen build system controls and sorts the input to the linker, so this is not an issue for our setup, but in the generic case, you really want to control it. Otherwise, just compiling the same thing on a different machine or on another day might end up with a different build. The output that we want to control is the so-called normative part of the binary. This is basically everything that you load into memory and that becomes active, or in other words, almost everything except for the debug information on the binary. So how do we achieve that? In the original build process, we capture a lot of the information that we require. We capture the original build output, we capture the original source code. We use a build server to create our packages, and the build environment that we use changes over time, right? People move to new versions, people have new requirements, they want to make new features, they install a new compiler, new libraries, and so on. So over the years, the build environment changes, but we need to retain that, so we capture that information, and our build system allows us to go back in time and can give us the information which specific package versions were used 2 years ago. So we have a system called Replicator that talks to the build server and understands which packages to use. It can pull out all the information in the packages and recreate the original build environment to help us build in there. We do that for each and every other patch and for each and every target build. And the embedded time stamp and the embedded host stamp we solve using slightly sophisticated binary comparison tool that understands where the information is and ignores that. The alternative approach here would have been to change the build system, not to embed that information anymore, but we wanted to have minimal impact on the build system. We wanted to retain it as originally as possible to limit the risk that we break something there. Okay, so I covered a lot of things. To summarize, we find hot patching to be a versatile reaction tool for security events. It enables us to collect customer data and gives us security and availability at the same time. And the risk limiting design that we use allows us to use it for many years going forward. Thank you for your attention.